Okay, ladies and gentlemen, it should be by this time that you have gotten your nuclear simulation finished, and you should be about halfway through the first, or you should have done the first page of that POGL activity. Hopefully, all that stuff is there for you. We're going to look over the notes um, that go with this, and then hopefully you can go back and, if you can, you can work and try to finish up on your back page of your POGL activity. If not, we'll finish that up next time. So we're going to be discussing nuclear radiation. Here's some of the things you should have found out today. Radioactive very simply means it's something that has an unstable nucleus. If you'll remember, there are protons and neutrons in the nucleus. It turns out that when the nucleus has a certain combinations of protons and neutrons, they're unstable, and what they'll do is they'll release particles and energy to become stable. So the energy that comes off from radiation, X-rays and things like that, atomic bombs and wherever, comes from these unstable nuclei. Any isotope of an element, you remember isotopes of elements are ones that have different numbers of neutrons. An isotope that is radioactive is called a radioisotope. Not all isotopes are radioactive. You're full of all kinds of isotopes in your body that are not radioactive, but a few are radioactive in you. Approximately 80% of all the radiation you're exposed to comes from natural processes. Most of them are in the medical industry. Um, the potassium that's in our bones and our muscles, uh, and the carbon that's all throughout our body, we are naturally radioactive humans. But things like X-rays, uh, a lot of the tests that they do in the medical industry, they put radioactive isotopes inside of a body so they can trace them and follow them to see what's wrong with a person. So most of the radiation you're exposed to just comes from outer space and just comes through from the sun and places like that. So radiation is a natural process. Um, helium nucleus, there are three kinds of radiation we're going to go through, and you kind of dealt with them in the simulation. The ones that were the easiest to stop, the ones that were stopped by the paper, were alpha particles. And what they are, if you look at the symbol, if you remember back to the symbol, top part's the mass number. That's the protons plus the neutrons. And this is the number of protons. We are not going to be worried about electrons in this chapter at all. We're just going to be looking at the nucleus of an atom, and because that's where nuclear chemistry comes from. Now that Greek symbol, I kind of make it like a fish. It looks like a guppy that's swimming to the left. That's an alpha, or we're going to write it as 4,2 helium. You'll see in the next lesson why we're going to want to do it that way. So because there's two protons, it has a charge of +2 and a mass of 4. They're big particles, therefore they cannot penetrate well. Your clothing will stop them, paper, skin. So it's really very hard to get poisoned or have nuclear damage to your body from alpha radiation because it just can't get in. Whenever a nucleus is too big, that's any element above 83 in nature. If you'll notice on our periodic table on the side of the room, those symbols have the radiation sign. Every element above 83 has that radioactive sign because their nucleus is too big. There's too many protons in there. And remember, positives repel positives. So in that little bitty nucleus, all those protons are trying to repel each other apart. And when they get too big, above 83, they just can't take it anymore, and they all blow apart with alpha radiation. But it's not very damaging, so we're okay with it. The next kind's beta, and beta, very simply, has a charge of -1. I know that's going to sound weird down here, and it does not have any mass. Essentially, it is an electron. So a beta particle is really an electron. So atoms shoot out electrons, and that was the ones that were stopped by the aluminum foil. You could have used wood. I don't think they used wood in the simulation. When there's too many neutrons in the nucleus, a neutron will get changed into a proton by emitting a beta particle. So if an atom shoots out an electron, it's almost like magic. It will become, a proton will become, a neutron will become a proton. So when a neutron shoots out an electron, it becomes a proton. And what that does will drop the neutron ratio. The third kind is positron. Now, you did not see this in the lab. It is the same penetrating power. It's weird. It's essentially a positive beta particle. It's a positive electron. It's called antimatter. So in this case, when there's not enough neutrons, then a proton gets changed back to a neutron and a positron is emitted. And last, gamma radiation, and it looks kind of like a fish standing on its head, or like a Y kind of, has no mass, no charge. All it is pure energy. And you need lead to stop it, and the small piece of lead that we had in the simulation didn't even stop it. You would have needed like 3 or 4 sheets of that lead before we would have been able to stop the gamma radiation. That's just pure, unadulterated energy. So it won't affect the charge or the mass. So not all isotopes are radioactive. So we said either the nucleus is too big, the nucleus has too many neutrons, or the nucleus has too few neutrons. That's our 3 reasons that atoms become radioactive. And radioisotopes try to emit. And your whole goal, if you're unstable, is to become stable. And you can do that by one of 3 methods. And we'll learn about that in the next lesson. This is a chart of the number of neutrons in an atom versus the number of protons. You will see in the early elements that the neutron to proton ratio is almost 1-to-1 ratio. When there's 10 protons, there's 10 neutrons. But you'll see as the atom gets bigger, because the protons, there's getting to be so many, we need more neutrons. Neutrons kind of act like spacers in between the protons, preventing them from blowing apart. But you'll see as the atoms get heavier, you need more and more neutrons to help stabilize the protons. Once you get up here to about 83, up here at Mercury, look, you need 1.5 protons for every, neutrons for every 1 proton. So if you had 80 protons, you would need 120 neutrons. This is what's called the belt of stability. These are the stable nuclei, the stable isotopes of atoms. Anything in that red area, that kind of pinkish area, those are unstable ones. So if an atom is not in the band of stability, then it will be radioactive. So I don't know how many exactly stable nuclei there are. I would say it's not more than a couple hundred. There's thousands of nuclei. There's thousands of isotopes, but only about 200 of the 1,000 or so are stable. So now we can go back and work on this second half of the lesson that will help us understand the rest of the material that you were presented. So enjoy that. So this is just a little chart that summarizes everything. This is a good place when you're doing your homework. If you need to know anything about the 4 kinds of radiation, you can go back and look at it. So in your lab, you should have found out that the alpha got stopped by paper, the betas got stopped by aluminum, and the gamma needs a lot of lead. They didn't give you enough lead to get that done in the lab. See you next time.